wait a little bit, a minute. So Giancarlo is going to talk to us about physical insights on ammonia mild combustion, implications for modeling and application. So we would draw a distinction between mild and what's called high-tech, high-temperature air combustion. Potentially, it is supposed to provide non-luminous flame and reheating of other products, or basically recovering of energy. So what I call heat and exhaust gas recirculation, either internally or externally. Yeah, it should go live by itself. Just don't put them out.
Can go this way.
No. Yeah, please.
Okay. Thank you. Thank you, Bassam, for the very nice introduction. I will start to introduce some concept related to ammonia mild combustion, starting from some basics, insight and fundamental properties of ammonia, also starting from what we already know on the basis of conventional combustion or turbulent premix combustion systems, something that we also heard yesterday or this morning, and I will relate them to mild combustion. So just few words on ammonia. As we already know, it has very low burning velocity, and for mild combustion application, ignition delay time is also very important. If we compare hydrogen or methane to ammonia ignition delay time, they are shorter in air or in also in diluted condition when compared with ammonia, and this is very important for application, as we will see later. So this kind of properties are very important for different kind of application. For ammonia, especially if we think to the very high autoignition temperature, and also very low burning velocity and the narrow flammability range. But also it's an issue is usually in conventional applications, the formation of a large amount of NOx. So if we start from what we already know on the Borghi diagram for premix combustion conditions on the basis of very well known Karlovitz-Dankler and Reynolds number, we have usually different combustion regimes as a function of length scale ratio and velocity ratio in turbulent intensity. And if we think to ammonia in particular, in premix combustion, usually we have very low burning velocity and large laminar flame thickness that, compared with hydrocarbon flames, if we want to apply, use ammonia in practical application, we can easily achieve systems with very high turbulent intensity and high Karlovitz number. This is also true if we have a turbulent velocity that is not particularly high. So in this diagram, we are moving from these thin reaction zones to something that is very close to a distributed reaction zones. We saw very peculiar example yesterday, but also this morning, of the characterization of the reaction zone in some conditions. So this is mainly true also for non-premix condition, when we can pass for the, if we have longer chemical time scale, we can pass from one regime to another. And so we don't have the existence of a flamelet regime. So this kind of systems with ammonia with very low burning velocity and large flame thickness will provide simultaneously condition that if we add that the Dunkel number usually is very low, will fit in the distributed regime. And this is usually very difficult to sustain because of the extinction and flames close to stability limits, especially for a point of view of different application, or if we think to gas turbines where turbulent is an important factor, and conventional flames also in laboratory are very difficult to sustain. So we have this kind of regime with large Karlovitz and small Dunkel. They are, of course, characterized in several TNF target flames. We know a lot of this, especially for conditions where Karlovitz and Dunkel are not so high, but I think that we are moving with several lab scale experiments toward this region that is very close to the stirred reactor. So we have for premix or non-premix combustion where flame propagation phenomena are important, we can, I think, characterize also for ammonia the interaction between turbulence chemistry and the transport. Of course, there was an important contribution in the previous years from several lab scales apparatus where Karlovitz numbers higher than 100, for example, were characterized, and simultaneously Dunkel number were reduced to reach these very peculiar and harsh conditions. So under this condition, someone can imagine that a reactive region is very difficult to exist, and I have imagined two possible scenarios. The first one is the one that I depicted up to now. So we have something that is some groups, Kaust and Lund and other people started to characterize. And in particular, mainly we have this increase of burning rate and flame service due to the enhanced scalar diffusivity. Of course, in this condition, we have important phenomena related to extinction. If we characterize, for example, the extinction of pure ammonia in simple counterflow regimes. We have, of course, during the recent years, several results with respect to this first scenario. For example, these are some results from Bill Roberts' group in Kaus, where they characterized the turbine burning velocity increase with respect to the laminar one in different conditions and also with different blends of hydrogen and methane. They found some correlation. The same was more or less done with very interesting results by the group in Lund, where we obtained similar correlation with respect to the turbulent fluctuations. So there is the possibility to a second scenario in this view, in this particular view. We can sustain this kind of combustion regime also by diluting the fresh reactants with burned gas. In this way, we can increase the flame robustness, and the reactive region can be stabilized if we have local preheating and vitiation of fresh gas. There is a pioneering work of Bassam with Norbert Peters, and they showed this reaction zone that was fairly distributed with patchy appearance of some scalars. In this case, it was OH radicals. Similar results were obtained also in other experiments. And they found that we don't have a propagating structure stabilization with this autoigniting kernel that growth and convect upstreams with the occurrence of this distributed ignition reaction zone. So if we compare this to what we have said before, I don't think that we have a corresponding diagram for this kind of scenario. Some people try to do this, and in particular, in this condition, we have that we have that if we diluted flames, these are some experiments and also computations. If you have the dilution of these flames with the products, we have that this kind of reaction regime do not exhibit typical extinction behavior. We have a dissolution of the extinction strain rate in mild that corresponds to a regime with a monotonic S-shaped curve. This kind of regime was also schematized by James Driscoll in his last review paper on progress in energy and combustion sites. He mainly said that experimental effort to achieve this large-scale distributed combustion by simply raising the turbulence level alone have not proven to be successful, but you need, of course, creating a dilution by burn gases. We have this kind of diagram where we can pass from normal combustion or lifted flame to what we call it globally distributed reactions. We have also some study by DNS studies by Minamoto by Minata, but also other people do that, where they recognize the appearance of these broadened and flameless simultaneously with the distributed reaction zones that I will call not globally distributed, but locally distributed ignition regimes. So we have these OH radicals that can interact, and they provide a low intensity and very distributed reaction zone. The same was done by in the past by Bassam and Paul Wedden, by passing from lifted flame up to mild combustion by changing the co-flow temperature and oxygen mass fraction. They observed this peculiar distributed occurrence of the OH star signal when compared to higher values of the oxygen mass fraction. So they said that mainly we are talking of a different regime where when we are moving from the 11% to 3% of oxygen. So the requirement for this distributed order ignition regime are mainly the rapid mixing between hot products and reactants. We need to do it in a shorter time than the ignition delay, and of course we need a large turbulence level with the recirculation zone then mix with the hot products, and this is necessary because we need to preheat above the auto ignition temperature, and the dilution of the reactants with hot inert products reduce the oxygen level, but at the same time we need high-speed injection of reactants to prevent the flame anchoring. Otherwise, of course, we can obtain different conditions that are more close to a flame-like behavior. So this kind of second scenario is called mild combustion, and we can characterize it mainly on the basis of two characteristic parameters. Usually we have conditions that are very diluted and very preheated in order to stay outside the flammability limits and to obtain mixed to auto ignition. And of course we need a highly diluted condition because we need a maximum increase of temperature that has to be lower than the auto ignition temperature. So if we try to understand which is the effect of this criteria on mild combustion for different energy carriers that we can use in mild, starting from hydrogen, I just reported 3, but we could have different curves. We can see that here I've reported the maximum adiabatic temperature increase with respect to the ignition one, and on the other axis the dilution level. So if we do if we do it, they are simple calculation. We can say that for hydrogen, for example, we are in mild condition for dilution level that are higher than 90%. This value is a bit lower if we are in methane, combustion condition. This kind of dilution level is lower of about 10% when compared to hydrogen for ammonia. So we can say that ammonia has a higher propensity to operate in mild combustion. This is mainly due to the particular characteristics of ammonia, as I said before, but of course we need to reach in this case, the auto-ignition temperature of ammonia locally or by externally preheating the mixture. Of course, in this case, from a practical point of view, this is very important because it means that you need to operate with lower recirculation levels, thus ensuring a lower dilution level of your mixture. Here I've reported the research on ammonia mild combustion. As you can see, we have up to now very poor literature for pure ammonia. It is increasing during last years, but with respect to the total literature on ammonia, I think it's quite below the target. Mainly several papers are focused on ammonia and hydrogen blends or blends of ammonia with carbon fuel blends. I saw very few papers on pure ammonia with mild. If we go to the reason is mainly related, I think, to the reactive structure that are stabilized. If we go if we go back to the insight on the reactive structure, this is previous results from the literature that we obtained in the past with methane. If we have a simple steady counterflow diffusion flame and we preheat the air and dilute the fuel at different level, we are moving the stoichiometric mixture fraction. We have this kind of broadening of the reaction zone as the dilution increase. So we obtained in the past these very peculiar results on a counterflow flame that we call a dot diluted diffusion ignition in order to distinguish this from a conventional diffusion flame, because we have these several characteristics related to the enlargement or the widening of the reaction zone, the depression of the pyrolysis region, and a sort of uncorrelation between the peak of heat release with respect to the stoichiometry. So if we try to do the same for ammonia, we done some calculation in a time-dependent mixing layer, and if we start from frozen conditions, we can characterize the first ignition. This is a igniting mixing layer where in this case we have pure ammonia and preheated air, so we don't have dilution in this case of the ammonia. So it's something very close to what the previous speaker called high temperature combustion. We observe a first ignition peak that is very close to the most reactive mixture fraction on the oxidizer side, where it's the high temperature. We have also a peak of heat release. If we go, so this is more or less close to 1 millisecond. If we go, if we follow the evolution of the process, we have this increase of temperature, and in particular in this condition, when we reach the stabilization time, we can note in this case a peculiar behavior that is related to the fact that at a time of around 0.05 seconds, we have this profile of heat release that are not related to the maximum of the at the peak temperature in the mixture fraction position. So if we characterize this kind of flame, we have most reactive and stoichiometric mixture fraction, but we can observe this kind of heat release stratification on the rich side of the flame. of course, this was obtained after a certain time. It was about 5 milliseconds. So at certain time, we observed this heat release profile that are in the fuel-rich zone and are not correlated to the maximum of the temperature peak. If we analyze some species profile, we can see that this process of heat release stratification starts where we form hydrogen, where we have a considerable hydrogen concentration in the igniting mixing layer. At the beginning, we have this correlation between heat release and maximum of temperature peak, but at around 3 milliseconds, we have that the heat release is shifted where we have this peak of hydrogen, so toward the fuel rich side. And if we think at the temperature peak, it was mainly in this region, so it was mainly related to the NO or OH radicals. If we do the same exercise for a case where we have high temperature, but the ammonia is diluted, in this case with nitrogen, but we can think to dilute it also with other burned gas. We observe at the beginning this very small ignition region for ignition delay times that are longer when compared to the previous case. So we are longer in the ignition. And this is the occurrence of the ignition process. If we follow the evolution in time, we have usually that we have a sort of, we can call propagation of the ignition front. Is not correctly a propagation, but we can see something like this. We have always that the occurrence of temperature is related to the temperature peak. So in this condition, we have that the heat release always follows the maximum of the temperature peak. So we observed in this case that the structure seems to be different with respect to the previous one. In particular, we don't have this kind of heat release stratification, but this diffusion ignition structure, this auto-ignition structure that convect and growth in time, the delta T is increasing during the time. We can see the same process if we move in the space. For example, this is a time coordinate, of course. We have this growth in this case of the diffusive structure because you can see that stoichiometric mixture fraction is moved toward the fuel-rich side. So we have in mild combustion this increase in the distance between most reactive and stoichiometric mixture fraction. And the ignition and stabilization times are longer when compared to conventional case. This is very important for application. So if we want to burn ammonia in mild combustion, we need to know these characteristic times, of course, for ignition and for the achievement of the maximum delta T in our system. In this case, we do not have in this case this kind of certification process, but usually the heat release rate is correlated mainly with the NH2 radical. Okay. So we have this kind of structure that are homogeneous or not independent on the length scale that we consider. These local structures are mainly different with respect to deflagrative or flame diffusion systems. And we have mainly structure that relies on auto-ignition. We tried to do some simulation of such systems, and the question was, can we directly, on the basis of this very basic knowledge on the reactive structure, can we directly apply turbulent combustion modeling paradigms that we usually use for premix or non-premix or partially premix combustion to this kind of scenario? Of course, we have different requirements. Auto-ignition, we have distributed reaction zone, very homogeneous with ternary mixing effect, and we have to take into account the fact that combustion is sustained for high scalar dissipation rate. So of course, we try to start by modeling such systems in the literature by using what was available, because the identification of new paradigm is not an easy task, and usually it required a deep collaboration between experimentalists and modelers. And of course, we need experimental data and DNS results on that. But I think that, as I said before, we don't have so many data for ammonia mild combustion in lab scale experiments. But I think that we will also need them in intermediate system that I can call scale bridging systems that are intermediate between canonical flames and systems that are more complex and close to reality. I think that this kind of systems are needed in order to obtain validation data on more complex geometries. These are some example of what we have done in Naples on the cyclonic flow burner that I will present also at the ASPACH conference. In particular, this is a cyclonic flow reactor where we obtain this kind of peculiar toroidal cyclonic flow inside the combustor due to the unique position on the air and fuel jets, and due to the position of the exit on the top. In particular, this kind of motion permits us to attain locally highly preheated and diluted combustion conditions. In particular, the ignition process at the beginning is started, and then when the temperature is higher than a certain level, we have this recirculation that ensure the occurrence of this peculiar mild or flameless regime inside the combustor. We've used it in past with several fuels. We are using it with ammonia. Here I've reported just some very brief results because they are also published in the literature. These are some results with ammonia. I want to point out that there are very few results, as I said before, with pure ammonia for mild combustion. These are one of them, and we reached very interesting and unique results by obtaining also NOx level lower than 100 ppm. In some conditions also, we reached single digit around the stoichiometry. We tried also to, yesterday I had a poster on that, we have also used ammonia hydrogen blends, and we investigated also the effect of using other more reactive fuels blended with ammonia, but up to now the best results in terms of NOx were obtained with pure ammonia. Okay. If we model this kind of reactor, we try to several turbulent combustion models that are usually applied in the literature to mild. If we do this for pure ammonia, we used tabulated chemistry with FGM or EDC or a recent development on partially steamed reactor. We can see that if we have measured the temperature along the axis in several points, we can see that agreements on temperature are quite good. I've not reported here one on the species at the exit, but they provided us very good agreement. But as you can see, if we see just the contours of OH, FGM, this is FGM and this is partially steer, they provided very results that are very different in terms of reactive region. If we do the same with an ammonia hydrogen blends, in this case we have 50% of ammonia in hydrogen, we can see that the disagreement is is worsened with respect to both the models, and this is true also for the species. We are investigating this kind of effect. If we increase the amount of hydrogen in the mixture, this kind of disagreement is getting worse, and we are trying to understand if this kind of disagreement is mainly related to differential diffusion effect or to the inclusion of the possibility of including, for example, the dilution of the internal dilution of the system in the modeling. I will report some other modeling works of MILE that, as I said before, they are very few works, but very important. There is a work by Ongim that tried to characterize a lean ammonia premix flame characteristics in miles through DNS. They found that this kind of heat release attenuation for mild regime were compared to conventional combustion cases. In particular, in this case, they found a dominant reaction pathway that indicates that in mild regime, the contribution of hydrogen-related reaction is promoted, and this is mainly due to ammonia decomposition. There are other contributions from that I reported of other group, in this case of Korean group, that they simulated the ammonia addition to a mixture of methane and hydrogen. They found that when ammonia is added to mild combustion, it shortens the preheating zone and increases the flow residence time. And in particular, by increasing the ammonia mass fraction, the flame lift-off is decreased. And the addition of ammonia to mild combustion, in particular, they found that provided an enhancement of the reactivity. The same group did the same by adding syngas to ammonia mild combustion. They found a reduction in they found that by reducing the proportion of ammonia, it's possible to increase the amount of OH produced, thus reducing the ignition delay. This is a results very similar to what we obtained in our reactor that I reported before, and it decreased the reaction zone extension. In particular, by increasing the proportion of syngas in the blend, it increased the maximum temperature area and decreased the reaction zone width. There are also other results from the Parentes group in ULB. In a semi-industrial furnace, they tried to model, they used ammonia and ammonia hydrogen fuel blends. They tried to model the system with through a reactor network on the basis of the CFD. They found some quite good agreement on the temperature, but large discrepancies in terms of NOx emissions. It was mainly related to the uncertainties on the rate constant of the kinetic model. Finally, there are some results of a group from Iran on that, where they characterized the reaction zone in a furnace used with pure ammonia, and they tried to reach, in this case, mild combustion. They obtained that for all the simulated cases, the Dunkeler number that they characterize lower the unity, and that they changed the world temperature, and this decreased the oxidized dilution level by helping in going in conditions that are closer to a distributed ignition regime. In particular, they found the minimum value of the world temperature required for ammonia to be stable. And in particular, they found that in the case of pure ammonia, this minimum world temperature is higher when compared to blends of ammonia with other fuels. And also, of course, this kind of this kind of modification of the fuel temperature also influenced the NOx emission. So in order to summarize just few insights on my talk, ammonia turbulent combustion usually in practical application can easily achieve high Karlovitz and high turbulence intensity with low Dunkel conditions, and this usually will fit it in the distributed combustion regime. But a possibility to stabilize ammonia pure ammonia reactive region is to dilute and preheat through burned gases the fresh reactants in order to increase the robustness of the reaction region. And it can be in principle be stabilized in this way. In this case, we have ammonia mild combustion that can be classified as a peculiar combustion regime that is different with the propagating structures that provide a distributed ignition reaction zone. So ammonia in conventional conditions showed a different evolution of the ignition pattern when compared with mild. This is very important for modeling aspects and for applications. As I said before, literature on ammonia mild combustion is scarce, and I hope that many people in in this community can try to model and to provide new data, new experimental data on both canonical and scale bridging systems. Thank you.
Thank you, Giancarlo, for this really interesting and stimulating talk. I'm sure there'll be some questions. Or is there any online as well? Okay, I could start. So it's no surprise that ammonia lends itself to mild combustion quite well for the reasons, of course, you articulated. In your work, have you looked closely at what happens to NOx? Of course, now you have two components. Of course, keeping the temperature down, so you're killing most of your thermal NOxes unless you have hot spots. But what are the measurements and how sort of is NOx being seen under these conditions?
You mean the measurements of NOx under
for ammonia?
Oh yeah, I showed it. For pure ammonia, these are mainly what we obtained. We have around stoichiometric something that is lower than, is around 50 or 60 ppm at 15% of oxygen. We try to, of course, also change the equivalence ratio at the inlet of the burner. If we go in lean, we have an increase of the NOx. Of course, if you go in slightly fuel rich, it's better to operate from a NOx point of view. You can reach single digit, but of course we have lots of unburned ammonia slip in the stack. So if we think to ammonia mild combustion, my opinion is that with respect to fossil fuel, when we need something like 0.6 or 0.8 of equivalence ratio to minimize NOx. From our experience, to obtain a very low NOx levels with the mild combustion, I mean, the best range is around the stoichiometric point. This was confirmed also with other blends with hydrogen. We found that if we add hydrogen to the ammonia, we have this decrease of the concentration of NOx always around the stoichiometric point. So this seems to be the best point to operate. Of course, we need temperature that should be higher than a certain level to sustain the process. For fossil fuel, this temperature is a bit lower, but if you operate with pure ammonia, this should be a bit higher than 1300 Kelvin. If you add hydrogen, for example, this range is extended. We can operate up to lower level of reactor temperature, but of course you have to deal with higher NOx levels. And but in this case, you enlarge a lot the stability windows of the operation.
So my question is, why, when adding hydrogen, you're ending up with more NOx? It's not thermal, is it?
Yeah. It's not thermal. We found that it's related to the formation of. When you add hydrogen, you have formation at the beginning of the process of OH radicals that compete with the NOx route, the reaction mainly between NH2 that are formed and OH provide you a route for the formation of the NOx instead of reducing them. This is the main picture that we obtained.
So would you think stratifying the NH3 and H2 may offer a solution?
Yeah, I don't have here some slides on that, but we have done this in the past by changing for example, the feeding configuration. We found that, in particular, due to some stratification effect, especially in this region where we have this interaction between the reactants and the recirculating products, we can lower the NOx level with respect to this non-premix, let's say, configuration. And this is due mainly to some stratification effects, because we have the creation of this reburning region where you have ammonia and fresh ammonia and NOx that are derived by the burned gases that helps you in reducing the NOx. Nice. So mainly stratification, I think it could be a proper solution. Yes.
Fantastic. Okay. Other questions?
The trend seemed to be consistent with the early results of Kobayashi's group and so on, where you get that minimum NOx around 1.1 or so. Do you, where the sweet spot is there? Do you have the complementary results for the ammonia emissions as well to see if you're landing the same?
You mean for this case, for pure ammonia? Of the ammonia slip, you mean?
Yes.
Yeah, we have it. I haven't reported yet, but if you go for equivalence ratio higher than 1.1, in all cases you have unburned ammonia that is more than, in some cases, is higher than 200 ppm. So, up to 1.05 of equivalence ratio, it is not too much, then it increases.
So I guess what it is that the sweet spot is still consistent with the Kobayashi
results. Yeah, we are almost in the same, in the same range. Yeah. It's between 0.95 and 1.05. Yeah.
Of course, that has an advantage that you don't have excess air that you don't need.
Yeah.
This is more of a comment. Just to clarify the theoretical definition and concepts. So premix scenario is one thing, and then in the non-premix, you talked about this 1D in the mixture fraction variable. I don't think we need another new definition of that regime, because it's just, if you have a non-premix system with the air side higher than adiabatic flame temperature, it is continuous. You have steady solution, and this is actually identified this classical Linian's paper. So it is a flame, and it's just a non-extinguishable flame.
So you're referring to this.
Yeah, right. That's right. This scenario, right?
Yeah.
So the second scenario where the temperature is.
I was referring to this non-premixed regime. This one. You're referring to this.
No. You had this 1D exercise.
Okay.
Of second scenario where the boundary temperature is actually, because the mixture is diluted enough.
Yeah.
That the peak temperature is a second scenario like that, right?
Okay.
So this is just a regular steady flame solution, except if you try to pick the like a reaction zone temperature as a function of scalar dissipation rate, you're not gonna find the regular turning point.
Yeah.
There's no, so there's no boundary between ignition and extinction branch. It's
Yeah.
just continuous.
Yeah. I said at the
So
beginning.
I
yes.
don't think there's any need to call it in a different way. That's all, just the semantics, but theoretical definition. Because you try to concoct a new word like Igni diffusion regime, but I don't think that's any necessary definition.
Yeah, but the structure that we observed is different with respect to what you call it, diffusion regime, diffusion flame.
This is a diffusion flame. That's what I'm trying to point out. And
Yeah,
you can actually
I don't think so.
use a flame net solution like that as a steady solution to describe this combustion behavior. If I know mixture fraction, I can describe all the reactive.
Yeah,
scale of
from my point of view of thermochemical state, I agree on that. Yes. Yeah. I was talking of of the reaction structure that seems to be different. That's what I said.
Gaetano, anything online? Okay. Maybe, yeah.
It was before me.
That's before, yeah.
Okay.
Okay, this is a great time to stop for a coffee break. Please thank the speaker again.
Thank you.